I'm very happy to introduce today's seminar speaker, Professor Chang. Ping is a Louis and Elizabeth Scherck Chair in Oceanography at Texas A&M University. So he has an interesting career path, and he first received applied math and mechanics from East China Engineering Institute. And he came to the US and then got master's degree in mechanical engineering from City College of New York. And then finally, he went to Princeton University and received master's and a PhD degree in atmospheric and ocean sciences. So Ping has received many awards, and most recently, he became a fellow of the American Meteorological Society in 2019. So Ping studies the dynamics and the predictability of the climate using both global and regional climate models. And he particularly focused on the role of the ocean and its interaction with the atmosphere in shaping the climate variability and change. He has done lots of seminal work in understanding the fundamental mechanism of tropical Pacific and Atlantic variability. And in recent years, he's been leading a very exciting project to develop an unprecedented set of very high resolution climate model simulation. And lots of exciting results are coming out from the project. He can tell us more about it today. Okay.
Thank you, Yuko, and thanks everyone for attending the seminar this morning. And I just want to say that it's really my honor and pleasure to come here again and meeting all the old friends, some of them unexpectedly. Yes, and also trying to make some new friends, hopefully, during this visit. So what I'd like to talk about today is the project we've been working on for the last 5 years or so, and on the topic of high resolution climate simulation. So I'll introduce the climate model in a minute, and so I revised the title slightly, so I added a CESM perspective because that's the model I'm going to be talking about primarily today. I'm not going to give a overview of the other model, even though we have looked at the other model too. So as you can see, lots of people contribute to this project. I have a long list of co-authors, and this project actually started with a international collaboration with colleagues in China, and for the reason is that China provided us tremendous computing resources for the project. And as you see in a minute, then to do this project, we really need large amount of computing resources. And but unfortunately, 3 years ago, the collaboration got terminated because the geopolitics reasons, you know. So we're no longer collaborating with the colleague in China. And so this project right now is entirely sponsored by the National Science Foundation. And the most recent simulation we've done is actually on TAC, the machine here. So I really like to acknowledge the support from TAC. Really helped a lot with this project. So let me just tell you a little bit about the model we're using. And so the model we're using is developed by NCAR. It's called a Community Earth System model. And we're not using the latest version. The latest version is version 2. And we're using a slightly older version of 1.1.3. And the reason for that is that, as you know, some of you may know, the newer version, especially in the atmospheric component, after they implement the new parameterization scheme called the club, and the model get a lot more expensive. It's very expensive to run. And we did some earlier comparisons. We don't see any advantage of running the version 2. So we decided to downgrade the version to stay in the version 1. and for computational efficiency purposes. So the model, the atmospheric component is called the Community Atmosphere Model version 5.3. And the version we're using is different from the standard CSM. We use the spectral element dicore, and which actually runs more efficiently for the high resolution configuration. So I want to make sure everybody understand that. So we're using the SC dicore, and horizontal resolution of the atmosphere model is 1/4 degree. So the standard model runs at 1 degree, for most of you know, right? 30 vertical levels, we did not change the vertical resolution, and we're not running the high top model. So the top of the atmosphere is 3 hectopascal. And the land surface, we're using version 4. Has the same resolution as the atmosphere component. And then has a river transfer model, Mozart version 1. And the major resolution increase is actually in the ocean. So the ocean model we're running at 1/10 of a degree nominal resolution, so about 10 kilometers globally. And the model has 62 vertical resolution. And we turn off all the physics parameterization. So there's no Jan McWilliams mesoscale parameterization. There's no submesoscale parameterization. There's no overflow parameterization. The only parameterization we're using is the KPP, the vertical turbulence parameterization in the model. And then the ice model, we're using the community ice code version 4, same resolution with the ocean. And we backport the CSM1 to the CSM2 coupler. So the model actually does have the same coupler, using the same coupler as the version 2 model. Now, because we changed the dynamical core, so there are some issues comparing our high resolution simulation with the low resolution standard simulation. So in order to make an apple-to-apple comparison, we also ran a low resolution version of the same model, so we can actually do an apple-to-apple comparison, right? So we have ported the code on 3 different platforms now. So we ported the code to the Sunway system in China. And so earlier simulation was done in China. And then because the shutting down of the collaboration, we migrated the code to Fonterra at TAC. And we spent a lot of time optimizing the code. And most recently, we ported the code to the Rancho at NCAR, the new computing system at NCAR. And we're very happy the code is actually parameterized really, really well. So on Fonterra, we typically using 800 CPU nodes, and we can run 6 years in a day with all the high frequency I/O. So it's a reasonably comfortable setting, and we can run quite large simulations. So just to give you a cost ratio between the high res and the low res version of the CSM model, it's about a factor of 100. So 1 year high resolution simulation is about 100 years low resolution simulation, right? So that's the ratio we're talking about. And that's the reason why the computing resource is very, very important. So just give you a eye candy view of the picture. I'm gluing 2 animation together. On the left is the high resolution version of the model. We're looking at the Western Pacific and Indian Ocean. On the right side is the standard low resolution model simulation, right? So you can see there's a huge difference in the ocean circulation structure. The high resolution model gives us a lot more mesoscale eddy activities and lots of new features which we don't get in the low resolution model. I'll come back to this point. It turns out this is actually a very important issue with the climate model. So in terms of the simulation, so far the simulation we have finished. So we did 3 main sets of simulation. The first set is the CMIP6 high resolution MIP ensemble. And so there are a couple papers published already. So we contribute. The first thing we did is contributing to the CMIP6 high resolution MIP ensemble, 3 sets of simulation, and 1 standard AMIP simulation from 1950 to 2014. And then we did 2 coupled simulation of 1950 control and plus transient climate simulation from 1950 to 2100. And then we also did the tier 3 simulation, which is the AMIP projection into the future using prescribed projected SST for the CMIP simulation, for the AMIP simulation. So that's the first set of experiment we finished. And the most expensive simulation is actually the second set. And so that's the standard CMIP deck set. So after we finish the high resolution MIP, one of the issues with high resolution MIP protocol is the control simulation is very short and the projection simulation is also short. So we decided to go back to the original CMIP design and follow the standard protocol. So we run pre-industrial control simulation for 650 years in a high resolution model. And then we branch out from the pre-industrial simulation, and then we did the one historical and future climate simulation under RCP 8.5 all the way from 1850 to 2100. So that's 250 years long. And then after that, we branch out from that simulation and did an ensemble of 9, 1920 to 2100 simulations. So adding the first set, we have ensemble of 10 simulations from 1920 all the way to 2100. And in addition, we also run a 10-member ensemble of future projection under the RCP 6.0 scenario. So now we have basically we have 2 ensemble of 10 historical and future climate simulation, one under RCP 8.5, the other under RCP 6.0. And then in addition, we did a single simulation of the RCP 4.5 and RCP 2.6. So we basically covered the 4 major scenarios of all the RCP future climate emission scenario. In addition, we did 2 climate sensitivity experiments because we want to understand how the high resolution model climate sensitivity differ from the low resolution model. So that's a very important thing to know. So we did 2, one transient climate sensitivity, the other one is the equilibrium climate sensitivity quadrupling CO2, run each experiment for 150 years. And in addition, we run 3 ensemble member of AMIP simulation from 1950 to 2015. So that's the entire set of the deck sets we have completed so far. Okay, now in addition to that, we also did something a little bit ambitious, and we actually did a decadal prediction experiment. So the DAC simulation I mentioned earlier are not initialized, so we're not using the observation to initialize the model. So in the third set of experiment, we're actually using observation to initialize the ocean model. So we actually completed the ensemble of 5 years and 10-member ensemble decadal prediction from 1970 all the way to the current 2020. So that's also a very expensive experiment. So the total simulation years we have done so far is about 6,000 years. And we have generated about 5 petabytes of data. You can see this is a major challenge. And we're trying to make the data available to the community. So if anyone interested in some of the data sets, I put a link here, and be very happy to talk to you more about how to get hold some of the data sets here. All right, just quickly give you a overview of the results. And so this is the a global mean temperature from 1850 all the way to 2100 and under RCP 8.5. So we're looking at two sets of a surface temperature. One is the surface air temperature. The other one is the SST, the sea surface temperature. So you see this this black line here, and that's the observation. That's the surface air temperature. And then this brown curve is the high resolution model simulation. And you can see the model actually agrees with the observation very nicely. And this is the low resolution version of the model running in exactly the same way. And you can see the low resolution model has a cold bias. It's about 1.5 degrees colder than the high resolution model. And this is the surface temperature. Again, we show two different sets of observation. One is from the ER-SST version 5, and the other one is the high-dye SST, which is this bluish color. And you can see our model is actually sandwiched in between the two observations. So the model, the high resolution model, is actually nicely capture the global mean temperature very nicely. The low resolution model is considered consistently too cold compared to the observation in this particular version of the model, right? So that's one thing we very pleased. And then the next things we look is the climate sensitivity. And of course, we like to know after we increase the model resolution, have we changed the climate sensitivity of the model? So this is just looking at the global mean climate sensitivity or the temperature response to the CO2 increase. So we analyze this transient 1% CO2 increase per year, and until the CO2 is doubled, right? That's the standard protocol for the transient climate response. And what we find is that the two model, despite the mean biases, right, mean temperature difference, the other difference in the physics, the global climate sensitivity remains remarkably similar, about 10%. So which is unexpected to some extent, right? So initially we were kind of disappointed, saying that we spent so much time running the model, and you know, the results seem to be similar to the low resolution model. So we decided to take a close look, and then you can look the regional climate sensitivity, right? Instead of looking at a global average, we can look there. Then we see some huge difference. So here's a map of the difference between the high resolution model and low resolution model near surface air temperature response to the CO2 increase, right? So this is the difference. So you can see the high resolution model is warming much faster in the Arctic region, and it's actually warming slower in the Southern Ocean, right? So this is a zonal average, a difference between high res and low resolution. You can see in the Arctic Ocean, the difference is approaching to 3 degrees. So the high resolution model is warming much faster. So does that really mean that the Arctic amplification is significantly increased in the high resolution model, right? If so, why that's the case? So so I'm going to show you two recent studies we did, focus in both the high latitudes, Northern Ocean, and also the high latitude Southern Ocean. And it turns out the high resolution model and low resolution behave very differently. So the first, looking at Arctic amplification. So the plot here is showing the time series here is showing the Arctic average, surface air temperature. So the black solid, the thick black line is showing the high resolution simulation. So this is the transient RCP 8.5 simulation from 1920 all the way to 2100, right? So that's the high resolution projected increase. And the low resolution projected increase is this thin line here, right? So you can see if you put a linear regression on this, For the high resolution model, we get about 0.8 degree per decade increase. The low resolution model is about 0.5 degree per decade. So you're looking at a difference about 30%. So the high resolution model is warming, projecting a much faster warming, or significantly faster warming, right? So not only that, this is the map of the warming rate. It turns out that in the high resolution model, the most of the warming actually occurs in the Pacific sector of the Arctic Ocean. In the Atlantic sector of the ocean, in fact, the warming is actually slower, which got us really curious why that's the case, right? So if we do an average of the warming over the Pacific sector, we're actually getting this blue curve here, right? And the blue curve, the thin blue curve here is from the low resolution model, average in the same sector. You can see there's a huge difference between the temperature change, the temperature between the high res and the low res in the Pacific sector. The Pacific sector in the high resolution model warms much faster. In comparison, in the Atlantic sector, actually, the high resolution model is warming slower than the low resolution model. So the difference, the stronger Arctic amplification in the high resolution model is primarily coming from the Pacific sector, right? So why that's the case? So here's another map. We're showing the sea ice fraction. On the left is the high resolution model. On the right is the low resolution model. I want you to focus on this, the Bering Strait opening here. And you can see that the sea ice in high resolution model is melting much faster than the low resolution model, right? So why that's the case? Well, it turns out that there's a huge difference in the low resolution model and the high resolution model representation of the Bering Strait through flow, right? So as you know, the Bering Strait is a very narrow strait. It's very shallow, right? It's only about 50 meters deep. So this is the symmetry in a representation in the high resolution model and the low resolution model. So the up panel here showing the high resolution representation of the bathymetry, the lower panel showing the low resolution representation of bathymetry. So in the low resolution model, we only have 2 grid points through the Bering Strait, right? So if you cross the Bering Strait, and you can see the difference, and the top panel is showing the heat transport in the high resolution model, and you see this intensification of the transport on the eastern side of the channel, right? And in the low resolution model, we only have 2 grid points, and this is what we get. We don't get any much, or we don't get much representation. So if you look how the Bering Strait heat transport changes in the future, so this is the comparison of model computed the Bering Strait heat transport as function of time. So the time is showing in the upper axis here, so 2000 all the way to 2100, and the bottom axis is showing the CO2 increase, right? So you can see the red line here is showing the transport simulated by the high resolution model, and the blue line is in the low resolution model, and this black thin line is all the CMIT model ensemble mean. So you can see that the high resolution model is simulating a much stronger heat transport through the Bering Strait, right? So our hypothesis is that it's really the improvement of the Bering Strait heat transport representation in a high resolution model causes the difference in the Arctic amplification. The high resolution model actually give you a faster warming in the Arctic Ocean. So then the next question is that, well, I mean, that's just comparing the high resolution and then the low resolution model, right? Is the high resolution model really getting better simulations compared to the observation? So we look all the observation. Unfortunately, it's observation near the Bering Strait is very difficult to find. We'll have very few observations we can get our hands on. So I'm showing you a few data model comparisons here. So the top panel is showing the the SSTs in the summer season. So the top left is showing the MODIS SST, which is a satellite product, right? And then the next to it is the high resolution simulation. And then we have the low resolution version of the simulation, and we have the CMIP5 simulation. And you can see that there's a very strong temperature gradient across the Bering Strait, and which is captured by the high resolution model, right? And the low resolution model gives a very poor representation of that temperature gradient, right? And the bottom here is showing the transport, the heat transport through the Bering Strait, and the blue line is showing the low resolution. Now, it turns out in observation, there's no direct measurements of the heat transport across Bering Strait. So the way the observationalists construct the Bering Strait heat transport is using a referred method. So they take a point measurement. There's actually 2 point measurements, A3 and A4. You see these 2 stars here. And that's where we have the mooring in the Bering Strait. So using a single mooring data, they're trying to reconstruct what the heat transport look like. So the observation showing black line here is using this proxy method to construct Bering Strait heat transport. So if we're using the same method in the model to reconstruct the heat transport, then we get this 2 dashed line here. And the blue, the red is showing the high resolution model, and the blue is showing the low resolution model, right? And then the solid line here is the model computed heat transport, because in the model, of course, we can compute the heat transport precisely, right? Because we calculate them, the model calculated exactly. So that's the estimate. And you can see overall, the high resolution model is slightly maybe overestimating the observed heat transport. And the low resolution model, depending on which method you're using, looks like it's underestimated heat transport quite substantially, right? And this is the flow transport in Sverdrups. And again, the high resolution model may be overestimating, and the low resolution model is definitely underestimating that. And this is the heat transport anomaly. So this is the climatology, right, as a function of calendar months. And we use the data from 2003 to 2015. And the bottom 2 panels is showing the anomaly. And so we're looking at the black line is showing the observation using the referred proxy method. And the red line is showing the high resolution model simulation. And the blue line is showing the low resolution model simulation. You can see the high resolution model actually capturing this increasing trend. And this is the sea ice near this Bering Strait region changes from 1980 to the present. And the black is showing the observation. The red is showing the model, high resolution model simulation, and the blue is showing the low resolution model simulation. Again, the high resolution model is actually capturing a better declining trends compared to the observation, right? So in general, it looks like the high resolution model does give you better representation of the circulation and the sea ice response during the historical period compared to the existing observation. So that's one thing we find. And the other thing, now let me switch the gear talking about the Southern Ocean, which is some recent work we've been doing. So this is, there's a lot of debates right now, or a lot of interest in looking at the Southern Ocean trends. So it turns out that if you look at the observation, right, in the Southern Ocean, so this is the trend at each grid point based on observation ERSST. So during the recent decades, from 1980 all the way to the present, and you can see, interestingly, in the Southern Ocean and in the southeastern tropical Pacific, there's actually a cooling trend in the ocean, right? And so this is the corresponding sea level pressure trends derived from the ERA5. And this is the the trends in the observed precipitation from the GPCP precipitation data sets. And you can see a very interesting dipole structure in the Southern Ocean in the SPCC region, right? So there's a poleward expansion of the precipitation. So apparently, if you look the low resolution model, and the low resolution model missed this cooling trends almost entirely. And this is not only the case for the CESN model, and this is the case for all the low resolution. If you look the CMIP6 model, most of the model misses this cooling trend. So that's a major issue. We don't quite understand why the model is doing so badly in representing this cooling trend, because this cooling trend really has a very strong implications for all sorts of climate phenomena, right? Including hurricanes and tropical cyclones. And interestingly, when we look at our high resolution model, and now we start to seeing these cooling trends, right? So this is the same analysis, and we're using 10-member ensemble mean and computing the trends in the global ocean. Now you start to see the cooling trends in both the Southern Ocean and in the Southeastern Pacific, right? Even though the amplitude is weaker, but part of the reason the amplitude is weaker here is because of the ensemble mean, right? Observation, of course, you don't have the ensemble. And this is the corresponding sea level pressure pattern. Again, a much better match with the observation. And this is the precipitation structure in the high resolution model. Now I'm getting something more similar to the observation, right? So that's very exciting. So then the question is why? Why the high resolution model is getting this cooling trend correctly? And so we're trying to look for causes. So the first we look at whether the atmospheric component is responsible for that, right? So we did a comparison between the AMIP simulation, low resolution and high resolution model. So the AMIP, of course, is a force with the observed SST, right? So we asked the question, if the atmosphere model is given exactly the same SST, are they getting a different response in atmosphere response, particularly in the Southern Ocean? So what we see, again, this is the zonal wind stress, global zonal wind stress everywhere around the globe over the ocean. And this is the low resolution model simulation. This is the high resolution model simulation. And this is the sea level pressure trends, and this is the precipitation trends. The period is slightly different because the AMIP simulation ends in 2014, right? We don't have the most recent SST available for doing the AMIP. So we stop at 2018, but nevertheless, you're getting a similar story, a very similar pressure pattern. And but if you notice, the difference between high resolution and low resolution actually is quite small. So the increase in the atmosphere model resolution does not seem to be is not the real cause for the changes in the Southern Ocean. We're getting a similar trends in the zonal wind stress, right? And in fact, the low resolution model, if you look, is getting an even stronger trends than the high resolution model. So the atmosphere model may not be the reason. And then so we look the ocean component. And so in this case, we're comparing two sets of ocean model simulation forced with exactly the same atmosphere forcing. So this is what we call the forced ocean sea ice experiment. So we forced the ocean model in high resolution and low resolution mode. And then we look the ocean response, right? So what I'm showing you here is the meridional heat transport in the Southern Ocean. Okay, on the left is the low resolution model results. On the right is the high resolution model results. So the top panel is showing you the time mean heat transport. The bottom panel is showing you the trends, right? So one of the interesting results you see is that the high resolution model and the low resolution model give us a different meridional heat transport. So in the low resolution model, we actually see more heat transport towards the South Pole, right? The positive is equatorwards, and the negative is poleward. So you can see the value of the mean heat transport indicated by this black line here is almost double the value of the high resolution model. So the ocean model, the low resolution model, is actually transporting more heat forward, right? And most of this, interestingly, most of this difference is actually because of the difference in the ocean eddy induced heat transport. So if you're partitioning the total heat transport into an eddy contribution component and a mean component, right? The mean component in the southern ocean latitude is about the same, or low resolution model is slightly lower. But look, the eddy contribution, which is this blue line here, the high resolution model actually gets a very weak contribution from the eddy, but the low resolution model is substantially larger, right? So that's really is a problem, because you see the low resolution model, we don't really have eddies. So we compute the eddy by parameterization, right? So all the eddy are parameterized. So that leads to a question whether the low resolution model is doing the right thing, right? So the high resolution model, of course, we turn off all the parameterization. We let the model compute the eddy flux by itself. And then another interesting thing is that not only the mean difference, but the trend is very different. So in the high resolution model, you can see the high resolution model does not project much changes in the eddy component of the heat transport, right? The mean changes, there's actually an increase, a poleward, equatorward heat transport in the mean and in the total. In the low resolution model, it behaves very different. So the projection, the trend of the heat transport is also very different, right? So that would indicate that because the low resolution model transporting too much heat forward, and we're getting warming in the Southern Ocean, the low resolution model. So if you look the simulated the sea surface temperature in the high resolution model and the low resolution model, we need to be careful because we're running the ocean only model, right? So we're using a Bock formulation. So to some extent, the sea surface temperature is restored to the air temperature, surface air temperature. So you expect the low resolution model and high resolution model should capturing a very similar sea surface temperature. But nevertheless, if you take the difference between the high resolution and low resolution model, you actually see that high resolution model gets more cooling in the Southern Ocean, right? So our current hypothesis is that perhaps the ocean heat transport and the cooling in the ocean, Southern Ocean, the different model physics in the ocean is really responsible for the trend, increase in cooling trends. Okay, so what about the future, right? So because there's a lot of debates whether the cooling trends in the tropics we observe now is going to continue, right? By the end of the century, whether we're going to see a warming or cooling. So we can take a look at that. So we computed the trends in the last 50 years of the simulation from 2051 to the end of the century. And this is the high resolution trend, and this is the low resolution trends. You can see that if you look the future, the high resolution and low resolution now is getting a consistent projection. We're going to see a warming in the equatorial Pacific. It's almost like an El Niño-like structure. And there's not much of a difference between the high res and the low res, right? So that leads to the question, what has caused the cooling trends in the most recent decades? And one of the possibility is the ozone, right? We know that the ozone hole in the Southern Ocean, in the Southern Hemisphere, is developing, started developing in 1979. So this is a snapshot of the ozone hole developments. You can see from the late 70s to the early 20s, we actually see a continuously expanding of the ozone hole in the Southern Hemisphere. Right, and in the most recent decades, there seems to be a stabilization. So one of the possibilities is that the ozone changes in the Southern Ocean is responsible for the strengthening of the winds along the Southern Ocean, and which has caused the ocean cooling, right? So we, in order to explore this possibility, we did a sensitivity experiment where in the model, since the model is getting the cooling trends correctly now, right? So what we can do is that we can do a sensitivity experiment by holding ozone constant, right? In the model, it's very easy to do. So we do a constant holding ozone experiment. So this is again observed. This is the SST trends in observation, and this is the high resolution model simulation. And we only take 3 ensemble because we did only 3 sensitivity experiment. So the 3-member ensemble give you a very similar cooling trends compared to the observation in the Southern Ocean. And this is what happens if you holding ozone constant. And then you can see that the cooling trend disappeared for the most part, right? And this is the wind stress response. So consistent with what we're thinking that if you're withholding ozone and keep ozone constant, then the strengthening of the winds in the Southern Ocean is significantly weaker, right? So that's currently is our hypothesis. The ozone is responsible for that. How much time do I have? Am I doing okay? All right, okay. So again, I'm going to switch to another topic now because there are lots of things we can talk about with it. So I want to talk about the extreme precipitation. And it turns out there's a big difference between the high resolution model and low resolution model in terms of simulating extreme precipitation. So here I'm showing you 2 observational data sets, and on the left is the HIDA X3, and this is the annual maximum daily precipitation. So basically each year you're looking for one day where you have the maximum precipitation, using that as a measure of the extreme precipitation, right? So this is the global distribution of the extreme precipitation, right? You see southeast US is one region seeing extreme precipitation, right? And then you see a little bit around the West Coast. And then there's the Asia monsoon region, large areas, we see a very active extreme precipitation. And this is using a slightly different criteria, 99th percentile daily mean precipitation, and using a different product. This is more recent using the GPM iMerge data sets, shorter data sets from 2000 to 2020. And this is the same plot. You can see there are lots of similarities between the 2 data sets, right? Where the extreme precipitation occurs. And this is doing exactly the same analysis, but using the low resolution version of the model. And you can see the low resolution model basically missed lots of the extreme precipitation, not much precipitation. And this is what happened if you look at the high resolution model. And the high resolution model is doing much better job. To some extent, it's actually doing perhaps a little bit too much, but we're capturing many of the spatial distributions of extreme precipitation. So I'm going to zoom in to the CONUS region over the US, right? So we're going to take a detailed look in this region here. So we're using even a higher resolution precipitation in the US. The precipitation data sets is much better than the global data sets. So we're looking at the 2 different data sets. One is from NOAA CPC observation, and the other one is the PRISM precipitation at a 4-kilometer resolution, right? You can see a detailed structure of the extreme precipitation. Some of the topographically or land elevation lock the feature along the Rockies, along the west coast of the US, right? And interestingly, southeast US turned out to be a region you see very large extreme precipitation. And this is the low resolution model simulation. Not very much, right? Muted structure. And this is the high resolution model simulation. You can see we're doing a much better job of capturing the extreme precipitation. And this is the 4-kilometer WRF simulation with prescribed lateral boundary condition from ERA5 reanalysis, right? And with the prescribing SST. And you can actually see that even our fully coupled model at a 1/4 degree seem to be able to capturing a lot of the structure in the extreme precipitation structure. So if you look at the PDFs, the rainfall PDFs, and divided it into the southwest in the upper panel and the southeast in the lower panel here, you can see the blue line is showing the low resolution model simulation. And the 2 black line showing the observation, and purple is showing the 4-kilometer WRF simulation. And then the red is showing the high resolution model simulation. And you can actually see the WRF compared to this particular data slightly overestimate the precipitation. And the high resolution global model is actually doing a remarkable job capturing the extreme precipitation, right? So now we have this data set, we can look the projection into the future, since we have the projection to the end of the century. So now we're looking at the extreme precipitation changes, difference between the last 30 years of the century versus the historical period time from 1976 to 2005. And this is the projected precipitation increase by the high resolution model. One of the surprise to me is that the majority precipitation, extreme precipitation increase is going to be in the southeast, not in the southwest, even though we expect a large amount of increase in the Adams River and phenomena like that in the Pacific sector. But for some reason, it doesn't seem to translate into a significant increase in the extreme rainfall. So this is a things we're investigating right now, and to see whether we can understand that. And this is the corresponding projection in the low resolution model, much muted response, right? And so interestingly, what we can do is that we can compare to the regional model projection, right? There are lots of downscaling analysis using, instead of using a global model, you can use a regional model. And with the approach called the pseudo global warming approach, right? You're assuming changes in the thermodynamical property of the atmosphere, but assuming the flow pattern does not change. So if you compare it to the WRF model, in fact, there's some consistency. The WRF model, the 4-kilometer, also projects a large increase in the southeast, right? But perhaps there's a more increase along the west coast. And one of the major difference we noticed that is actually in the southwest desert area over here, what high resolution model projects no increase or maybe even slight decrease in the extreme rainfall, but the WRF actually projecting a quite significant increase. So that's interesting difference, right? And whether this difference is caused by the inconsistency in the lateral boundary condition or something else is not clear. So that's something we're investigating. So the question is why the high resolution model is doing much better than the low resolution model, right? So we dig into this issue a little bit in our research and trying to find out why that's the case. So it turns out that when we increase the model resolution from 1 degree to 1/4 degree, there is a very significant change in the partitioning of the parameterized and resolved precipitation. So the high resolution model, when we increase the high resolution model, there is a significant increase in the large scale resolved precipitation. So this is showing the difference, the total extreme precipitation difference between the high resolution model and the low resolution model. And this is showing the resolved large scale extreme precipitation between the high resolution and low resolution model. And you can see the pattern is very similar, and also the magnitude is very similar. So which means that the majority of the change we actually see in the total extreme precipitation is actually coming from the the large scale precipitation change, right? So if you calculate the percentage of the extreme precipitation contribution from the resolved large scale versus the parameterized. In high resolution model, it turns out 92% of the extreme precipitation is coming from the large scale. Only about 8% is coming from the parameterized. And in the low resolution, the percentage is very different. 74 come from the large scale, and the 26 is coming from the parameterized. Right. So in other words, the low resolution model depends to a quite significant extent on the parameterized rainfall to compute it, to simulate extreme precipitation. Right. So if you look the region of the U.S. and this is the ratio, right, between this is average in the southwest and this is the southeast, and this is how the partitioning of the large scale versus parameterized precipitation changes with time. So from 1920 all the way to the 2100, and we see that in the high resolution model, this partitioning, the ratio basically stays pretty much the same, does not change. Particularly in the southeast, you can see this the ratio between the large scale and parameterized precipitation is about 5%, and it's a constant. Doesn't change as the warming increase, but the low resolution model actually showing increase, which means in the future, the dependence on the parameterized precipitation is even larger under the warming conditions, right? So this is another interesting result we find, and we find that the reason we actually high resolution model, the quarter degree model seem to be getting better results than the low resolution model. Perhaps is due to this change in the partitioning. The high resolution model in the mid latitude lands relies on more on the large scale resolved precipitation. Compute is extreme. So finally, I have a couple of slides showing the hurricanes, and since we're running quarter degree model, right? So we're getting a much better representation of the hurricanes on the global domain. So this is the comparison between the hurricane distribution over the globe from the observation and our high resolution model simulation. And you can see the high resolution model is doing now a decent job in capturing the observed structure with some caveats, of course. One particularly bad feature of the model is in the South Atlantic Ocean, the model producing way too much hurricanes. And we're not the only model, many models doing the same thing. And this is interesting things we're still trying to understand. And the other thing you can see is that the model actually underestimates the activity of the hurricanes in the Atlantic Ocean. So this is an interesting map, and my colleague Dan Fu made this map. So this is the hurricane or tropical cycle related precipitation along the coast. So the landfalling hurricane produce precipitation, and this is the average of the climatology of all the landfalling hurricane rainfall distribution along the coastline, along the globe, right? So you can see a lot of the region in the Western Pacific, of course, expect a large impact of the tropical cyclones. Some of the Indian Ocean, North Australia, over our side, the Gulf Coast, East Coast of US, and Central America also have a lot of precipitation related to the tropical cyclone. And this is the model simulation. And again, the model is doing a quite decent job in reproducing the hurricane-related rainfall. Not perfect, right? And one of the major issues, again, is in our region. The model underestimate the rainfall quite significantly. But over the Western Pacific and the Indian Ocean sector, the model is doing quite decent job, right? So now with this, we can actually ask the question whether the rainfall is going to increase in the future. Hurricane-induced or Pacific tropical cyclone is going to. So I'm showing you two maps here, and on the left is showing the total number of tropical cyclone globally simulated in the model. So we actually see a decreasing in number of hurricanes as the global warming continues, right? But interestingly, if you look the hurricane-induced or the tropical cyclone-induced the rainfall along the coast over the land area, we actually see a significant increase. So which means that even though we're getting less tropical cyclones, but the tropical cyclone related rainfall is expected to increase quite drastically, right? So let me just summarize what we have done. We have lots more results and don't have time to show. I'll be very happy to discuss with you if you're interested in this data sets. And so let me just make a few points. And I think we made some breakthroughs in the global climate high resolution simulations. And we completed a DAC set, which is unprecedented. We believe we're the only group currently producing these data sets. And we also have initialized multi-year decadal prediction experiment, which I don't have time to show any results, unfortunately, today. And I think this data set is going to offer an excellent opportunity for us to evaluate the potential value of the high resolution climate model simulation. And we're already seeing some of the benefits. For example, I don't have time to show you all the results, but we actually find that some of the biases of the common biases we're actually seeing in the model. For example, the SST bias, mixed layer bias, the upwelling bias, and even the Labrador Sea deep convection bias is actually getting much better in a high resolution model. And also, I mentioned a few regional circulation feature like the Bering Strait, right? The Bering Strait transport is getting more realistic, we believe, and that can lead to upscaling impact like the Arctic amplification. Trying to show you. And then I also mentioned this cooling trends in the Southern Ocean, and we believe this may be related to the ocean heat transport issues. That's current hypothesis we have. And we also, when we evaluate the high resolution decadal prediction, we actually see the useful scales even in predicting atmosphere river and the TCs, which I don't have time to show that today. And finally, I show you one example, the improvement we're actually getting in extreme precipitation. We see some really encouraging improvements. So one of the lessons we learned from this exercise, a very expensive exercise, is that the increasing the model resolution can lead to improve the physics. And so a lot of improvements we're actually seeing we think it's really related to reducing the dependence of the parameterization physics. When we rely less on the parameterization, we're actually getting better results. We think it's both the case for the extreme precipitation as well as for the ocean heat transport. So the challenge, finally, one thing we learned from this exercise is that tuning high resolution model is really difficult, because it's just so expensive. We made a lot of effort trying to balance the top atmosphere radiation, because when you make the long simulation, you need to balance the top atmosphere radiation. Otherwise, the model is drifting, right? And it turns out that that's a daunting task. You have to spend a lot of time doing that. And in fact, our model is not perfectly balanced. There's some issues here. And the other one is that the intermodal comparison is going to be a major challenge. And right now, we're the only group, as I mentioned, doing this kind of experiment. So we'll basically rely on one model, right, to tell us what is wrong, what is right. And the hope is that we're going to get more models in the future so we can do a model intercomparison. And last but not least is the data storage and sharing, which is a major challenge. I mentioned that we generated about 5 petabytes of data sets already, and we're probably going to generate more. So how to share and how to make the community use this model is a challenge. So I stop here. Thank you very much.
Thanks. I guess I wonder about the part of understanding the physics better with a higher resolution. Now, when you do the comparison between the low and the high resolution, you showed that there's a cold bias in the low resolution model. Presumably, you then fix that bias when you do the later comparisons. So it's not like the low resolution model has a lower RMS because it's already not working. So you patched that up?
Yes, the low resolution model is already that's a well-known problem. So for a long time, we know that the climate model have a cold bias in the open ocean, but a warm bias is along the upwelling region. And when we increase the resolution, and some of those biases actually reduced. Physically, we actually just published a paper trying to understand what causes the change in the bias. It turns out has something to do with the KPP parameterization, the vertical heat flux in the ocean. When we run in a high resolution model, the vertical heat flux is actually changed quite a bit.
Right, but so you already know that there's a bias, right? And what I'm asking about is that if you know that there's a bias, presumably there's not just a bias in the mean, but there's also bias in the
variance.
So later when you compare precipitation, right, then the low resolution model is not going to work, right? So it's like it's being a little bit unfair to some extent.
Right. I mean, that's a part of the reason, right? It's a part of the reason because the precipitation is not all influenced by the mean state bias. And
sure,
it should be.
Sure, but it seems like there's a version of the low resolution model that could be tuned to have higher variability that might be a fair comparison.
Well, the certain things you by tuning you cannot. If, for example, hurricanes, right? Doesn't matter how you're going to tune the hurricanes. That doesn't matter how you're going to tune the low resolution model. The hurricane is not going to be.
But it's also not really made for that, right?
Right.
So you got to compare apples and apples.
There are certain.
So when you look at the actual effects then of the resolution, it's clear you get more eddies, right?
Right.
And so there, it would seem like you want to have an understanding if your resolution is good enough, right? And so what I'm wondering there is, sure, like you increase the resolution further, is that going to give you convergence? And again, right, what do we know about the eddy parameterization?
Right. I mean, that's an excellent question. Unfortunately, we don't know. I mean, the problem is that.
But surely people have isolated that problem with the eddies, that you have some feeling.
In order to see the numerical convergence, right, of the solution, you have to continue increase our resolution until the numerical solution becomes stable, no longer sensitive to the resolution increase.
Right, but you don't have to do that on the full system, right? You can just look at the ocean eddy system and then take an isolated system.
Even for the ocean eddy system, I think it's going to be a challenge. I mean, people doing the large eddy simulations, directly pushing or direct numerical model simulations. I mean, you can push the resolution down to very fine scale, but only in a limited area. So it's very hard to do a global direct numerical model simulation, given the computing resources we have.
Right, but presumably you have some understanding of the scaling, and you can sort of see if you get the right kind of scaling with this model.
Yeah, I mean, we can take a look the energy spectrum and to see whether the energy spectrum is consistent with some of the estimate from the observations, right? And then the other issue is that
and does it look like that? Does it look like you go in the right direction?
I think so. Yeah, we're definitely going to the right direction. And the other thing is that we also have to have high resolution observations too, right? So for a lot of the ocean stuff we're doing, and we rely on satellite observations, for example, and there's going to be a new satellite mission launched, right, called a SWAT, and hopefully we'll get even better global resolutions for the sea level height variability, and that would allow us to look the ocean eddy and some mesoscale, and even with the high, the SWAT mission, I don't think we can quite resolve the sub-mesoscale variability. So down to the very fine scale, it's going to be a challenge.
Thanks for a great talk. So you showed the like the ocean gateway transport and sort of hinted at coastal upwelling effects is like really important. So with that in mind, is there any benefit to having like a variable resolution where you have high resolution along coastal areas and maybe coarser resolution out in the open ocean, or is it too complicated?
Yeah, I mean, that's definitely a potential way of, you know, if you cannot afford to running a global high resolution model, perhaps you can running the regional refined model. One of the issues with that kind of approach, again, is the parameterization. We have to develop a scale aware parameterization, right? Because you need parameterization in the coarse resolution region. And you don't really need those kind of a parameterization when the resolution gets very high, right? Because you resolve the process. So how you transition from coarse resolution region to the fine resolution region, that's a challenge. So we'll have to think up of ways to develop parameterization which varies as spatial scale, right? So there are a lot of work trying to be, I mean, the atmospheric community, you know, has been trying to do this for quite some time, right? Regional refined approach, how to develop this scale aware convective parameterization. The ocean community, I think it needs to, I mean, if we want to use this kind of approach, I think the oceanic community basically needs to do a similar thing because there's going to be this issue when you transition from a coarse region to a fine region, and how you're going to represent those physical process. It's not straightforward, I think. Well, I like the system you have.
Thank you. Very impressive work. Thank you. Just a quick comment. The SWOT actually has been up for a year now,
right.
And the noise level seems to be much better than what people had expected. So you can actually go down to maybe just the two kilometer level, which was not what people had thought.
Okay,
so
good.
It's quite impressive.
Okay.
But a question back to the Arctic. We think about the Pacific water as once it enters Bering Strait, it subducts, and basically it forms a layer that's actually isolated from the surface layer through the halocline. And so I'm not sure whether how much. I mean, there might be some effect, but how much of that is really, even if the transport has increased, whether it really that's
right.
the main cause of the Arctic amplification, because it would have to be other processes that will bring that water to the surface
right.
across the halocline. And I'm also this dipole where you see the cooling on the Siberian shelf seems to me, which you could accomplish if you have an increase in ice export factory, right? So there's only ice that basically will be very briefly be produced and then basically get advected and then melts.
Right.
So I'm wondering whether it isn't really surface processes and something to do with fresh water and the sea ice actually itself, which is very fiddly.
Yeah, I mean, that's an excellent question. I mean, this is something we're trying to look into and look the three-dimensional subsurface ocean structure, how the water after getting to the Bering Strait and where the water goes, right? I mean, you know, one of the issue again is trying to get the observed data sets available to compare things like that. So we're using EN4, which seems to be a standard data sets people using, looking at the observations. And, you know, so far we see some consistency between, it looks like the high resolution model does get a better vertical structure compared to the low resolution model. And that could also contributing to the improvement we actually, to the difference we actually see. But I think we need to do more analysis trying to really understand it. But that's an excellent point. I mean, a lot of the physical process, I think a lot of issues, there are a lot of people focusing. I think the purpose of this study we're trying to point out is that there are lots of emphasis in the Atlantic sector in terms of the Arctic amplification for the obvious reason is that Atlantic opening transporting a lot more heat, right, into the Arctic Ocean than the Pacific. So the Pacific, to some extent, is being ignored by the research community to some extent. So one of the reasons we're trying to publish a paper on this is trying to say that, hey, you know, the Atlantic side of the Pacific side may be equally important too. We should take a look at that as well, right? But thank you for the question. Well, you have a better football team, I guess, than us.
All right. Thank you so much for that talk. Just a clarification. In increasing the resolution, did you also consider, did you parameterize the aerosol, important of aerosols in this, or did you resolve the aerosols?
Unfortunately, this is a question beyond my knowledge. There's an aerosol model, I believe, in this setup, but a lot of the aerosol was prescribed as a forcing agent in this model in a historical period. I'm not sure how in the future emission how the aerosol forcing is. And I don't believe the model actually have direct aerosol input. So I'm not sure how to answer that, to be honest. So sorry. I mean, I'd be very happy to get back with you with more answers, you know, after I talk to my colleagues at NCAR. Yeah, I'm not an aerosol person, so I can't. I'm not able to answer this. Right. 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 Yeah.
Part of is the application process. So, you know, having profiles and having the model resolve aerosol emissions actually provides much in depth.
Right. 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 Yeah, I can't answer that, but you know, the configuration of the model we're using, as I said, is very similar to the standard, the CESM 1.0. So we didn't change the aerosol component of the model. So we basically kept the configuration the same as CESM 1.0. But I can get back with you on the more details. Yes, sure.
Okay, let's thank again. Thank you so much.